Hi, this is Philip Armstrong presenting about thermonuclear reactors. Thermonuclear reactor. Thermonuclear reactor in-depth technical overview. A thermonuclear reactor, or nuclear fusion reactor, is designed to harness the energy produced by nuclear fusion, the process that powers stars like our Sun. Unlike nuclear fission reactors, which split heavy atomic nuclei, fusion reactors combine light atomic nuclei, typically isotopes of hydrogen, to form a heavier nucleus, releasing vast amounts of energy in the process. The successful development of thermonuclear reactors could provide a nearly limitless, clean, and sustainable source of energy. Fundamental principle: nuclear fusion. Fusion reaction. The most common fusion reaction under study involves the isotopes of hydrogen, deuterium, and tritium. The reaction is: deuterium plus tritium yields helium-4, a neutron, and 17.6 mega-electron volts of energy. Helium-4 is a stable product. The neutron carries a significant portion of the reaction energy. 17.6 mega-electron volts is the energy released per fusion event, significantly higher than fission energy on a per-nucleon basis. Conditions for fusion temperature fusion requires temperatures of tens of millions of degrees Celsius, often above 100 million degrees, to overcome the Coulomb barrier, the repulsive force between positively charged nuclei. Pressure. High pressure is needed to increase the likelihood of collisions between nuclei. Confinement time. The plasma must be confined long enough for fusion to occur. The Lawson criterion, which is the product of the density of the plasma, temperature, and confinement time, must be met to achieve net positive energy output. Plasma state. Definition. Plasma is a state of matter where gas is so hot that atoms are ionized, meaning electrons are separated from nuclei. This results in a mix of free electrons and ions. Plasma dynamics. Controlling plasma is challenging due to its high temperature and its interaction with magnetic fields. The plasma tends to be unstable and can undergo various instabilities, which must be managed to maintain the conditions necessary for fusion. Magnetic confinement. The tokamak. A tokamak has a donut-shaped or toroidal chamber where plasma is confined. The toroidal field, generated by external coils, wraps around the torus, keeping plasma particles moving along circular paths. The poloidal field, generated by the plasma current induced in the plasma itself, combines with the toroidal field to create helical field lines, further stabilizing the plasma. A current is induced in the plasma, which not only helps in confinement, but also heats the plasma through resistive heating. Key parameters include the aspect ratio, which is the ratio of the major radius, from the center of the torus to the middle of the plasma to the minor radius or plasma thickness. This affects the stability and confinement. Magnetic shear, the variation of magnetic field strength across the plasma cross-section, helps prevent certain instabilities. The safety factor, or Q, describes the stability of plasma and is related to the twist of magnetic field lines. However, there are challenges. Instabilities such as MHD or magnetohydrodynamic. Instabilities like kink and ballooning modes can disrupt the plasma. Neoclassical tearing modes, or NTMs, and edge localized modes, or ELMs, can lead to a loss of confinement. Additionally, handling the immense heat and particles escaping from the plasma, particularly in the divertor region where these are removed from the tokamak, remains a significant challenge. Inertial confinement fusion, or ICF, involves rapidly compressing and heating small pellets of fusion fuel, usually a mixture of deuterium and tritium, using high-energy lasers or ion beams. The National Ignition Facility, or NIF, uses powerful lasers to implode fuel pellets, heating and compressing them to conditions necessary for fusion. There are two main methods: direct drive, where lasers directly target the fuel pellet, and indirect drive, where lasers target a hole round, a cavity surrounding the pellet, which then emits X-rays that compress the pellet. There are challenges in ICF as well. Ensuring uniform compression or symmetry is critical to achieving fusion. Ignition, achieving a point where the fusion reactions release enough energy to sustain further fusion without external input, is another major hurdle. Energy output and breeding tritium are also important considerations in making ICF a viable energy source. Energy capture, neutron utilization. Neutrons from the fusion reaction carry most of the energy and can be absorbed by a surrounding blanket material to generate heat, which can then be used to produce electricity. Heat exchangers transfer the heat from the blanket to drive turbines, similar to conventional power plants. Tritium breeding, lithium blanket, surrounds the plasma chamber and captures neutrons to breed tritium through reactions with lithium. For example, lithium-6 plus a neutron produces helium-4 and tritium. Tritium recycling. Tritium produced in the blanket is extracted and fed back into the plasma. Materials and structural challenges. Plasma-facing materials must withstand extreme temperatures, neutron bombardment, and erosion. Tungsten, often used for its high melting point and low sputtering yield. Carbon-based materials, such as carbon fiber composites, used in some diverter components, though they tend to absorb tritium, which is problematic. Superconducting magnets, low-temperature superconductors, or LTS, such as niobium tin, used in large, steady-state magnetic fields. High-temperature superconductors, or HTS, emerging as potential candidates for higher field magnets, which could reduce reactor size and increase efficiency. Neutron damage, embrittlement. Neutron bombardment can make materials brittle, reducing their lifespan. Transmutation. Neutrons can cause atoms in the reactor materials to change into other elements, affecting material properties. Current and future projects. ITER, the International Thermonuclear Experimental Reactor objective, demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. Scale will be the largest tokamak ever built, aiming to achieve a burning plasma where the fusion reaction is self-sustaining. Challenges: construction complexity, cost, international collaboration, and achieving first plasma expected in the 2030s. JET, the Joint European Torus contributions, has achieved record fusion power output, providing critical data for ITER. Research focus, testing materials and scenarios for ITER and future reactors. Demo. Next step. Following ITER, Demo is planned to be the first fusion power plant to generate electricity for the grid, building on ITER's results. Engineering challenges will focus on achieving continuous operation, full tritium breeding, and integration into the power grid. Spark and Arc. Private sector. Companies like Commonwealth Fusion Systems are working on compact tokamak designs using HTS magnets, aiming for quicker development cycles and lower costs. Conclusion and prospects. Promise of fusion. Fusion represents a potential energy revolution, offering abundant fuel from hydrogen isotopes, minimal radioactive waste, and no greenhouse gas emissions. The road to practical fusion power is fraught with scientific, engineering, and economic challenges, but advances in plasma physics, materials science, and superconducting technologies are steadily paving the way. Future outlook. If successful, thermonuclear reactors could provide a stable, long-term solution to the world's energy needs, reducing dependence on fossil fuels and helping to combat climate change. Continued international collaboration, public and private sector investment, and breakthroughs in key technologies are essential to bringing fusion energy to fruition. Include my picture.